Hi again everyone. In this video we're going to discuss one of the applications of double integrals, and that is how to determine the area of two-dimensional shapes and two-dimensional regions. Now we know from high school that single integrals can also compute areas of regions, and double integrals just an extension of those ideas, and this video is just going to consider the following example where we are asked to calculate the area bounded by of the region bounded by these three curves. Before we get to that though, there are lots of important applications where the area of a two-dimensional shape or region is required. For example, if we want to determine the centroid of a two-dimensional region or shape, then we need to calculate the area of that region or shape first, and double integrals can be used for that. So for this particular example, I'm going to sketch these curves and actually get a good geometric understanding of the region that we are working with here. So I'm just going to draw a rough sketch. So here's the line y equals x. Here's the line y equals x on 2, and the third curve is y equals root x. So there's our three curves there. Again, it's a pretty ordinary graph, but hopefully you get the idea. So let's look at the region then bounded by these three curves. Well, if I look at the region that's enclosed by these three curves, well, that will be the region whose area we wish to calculate. So I'm going to denote this region by omega. Now you may be looking at this picture and going, well, hang on, I can easily calculate the area in this region, omega, just by using single integrals. Yes, I agree with you, you can do that. However, one of the nice things about this particular example, well, you're asked to use double integrals, and this forces you to think about the structure of this omega set. In particular, if you look at this omega set, it's not what's known as a simple region. Okay, so what I can realize though, hopefully, is if I look at the intersection, the x-intersection coordinates of these curves, what I can do is actually slice up my region into two simple subregions. So if I call this region omega 1 and this region omega 2, then you can see this region here is bounded by these two parallel lines, parallel to the y-axis, and these two non-parallel lines. Again, omega 2 is bounded by these two parallel lines to the y-axis and these two non-parallel lines. So to calculate the area of the whole omega, I'm going to calculate the area of omega 1 and omega 2 and add the two areas together. So it's important to first of all realize that, note, our original region is not a so-called simple region. But omega 1 and omega 2 are simple. So, how do double integrals come into this? Well, the area of omega is just the double integral of the constant function 1 over omega. Now, because we have this relationship here, we can split this up into individual integrals over omega 1 and omega 2 and just add the two integrals together to form the total area. Now, to set up these integrals properly, we need to mathematically describe omega 1 and omega 2. So, from our graph, we can describe these two regions. Well, let's consider omega 1. It's all those points such that x is between 0 and 1, and y is between these two functions here. So the top function is y equals x, the bottom function is y equals x on 2. Okay, and let's look at omega 2. Well, omega 2, the x points are between 1 and 4, and the y points are between these two functions. So y is between x on 2 and root x. So let's write that down. So now we've got all we need to set up and evaluate these two integrals. So let's do that. So thus, we obtain the following. The area of omega. Okay, so now I'm just setting up my two integrals. So this one will be in the following way. Okay, so it will be dy dx, and similarly, 4 and 1. So all we need to do now is evaluate these in the usual manner. Now these are really simple, so you can actually do the first integration by inspection. We're integrating 1 with respect to y, so we're actually going to get x minus x on 2 in the inside integral. Now x minus x on 2 is just x on 2. And similarly over here. Now, if you're using, of course, single integrals to solve this problem, you would actually start with this. So you can see now how it lines up with the simple ideas you would have learnt at school. But remember, the basic idea behind this problem is to get you to try to identify simple and non-simple regions. Okay, so now it's just a matter of doing the last integration. We'll get something like this. And then it's just a matter of substituting in the values and cleaning up a bit, and we'll get an answer of 7/6. Now remember, we are calculating area here, so I'm going to put it in square units.